JSR107.
Right. All right, thanks. Hi, everybody. I'm Ben.Cotton. I'm a programmer here at Credit Suisse, and I work specifically on the capital markets technology team. I'm also Credit Suisse's representative on JSR107, which is the new Java caching API standard. If you notice on the slide, I have the word new in quotes. That's because JSR107 is new only in its most recent sense. The specification was originally the original specification went out in 2001, but for whatever reason, the spec became inactive, and is usually the case with the urgency to push forward new standards. That urgency usually comes from an existing delinquency of other standards, and that's especially true here with JSR107. Its new urgency to get pushed as a standard is because Java is frankly a weak participant in capital markets caching solutions. Most of my clients, the big sell-side banks, when they want to consume price ticks from the ECNs, they're going to use something like KX Systems, KDB, and they're going to use Q operators, Q programming language operators, to process those low latency events, because Java frankly hasn't stepped to the plate with a sound and complete solution for caching in capital markets use cases. What I want to do is share with you some of the history of those delinquencies, some stories about the physics and the mathematics of low latency as it applies to a capital markets use case. We have one dramatic story I think you'll find pretty entertaining. I really like this Java users group. I've only been to a couple of meetings, but they've been really, really spectacularly entertaining. I went to the Scala presentation, very well done and entertaining. I went to the gentleman who gave the functional thinking presentation, spectacular. And of course, I went to your presentation, and when you were using JMS on the public internet to steer that race car from your iPhone, I thought, oh wow. So anyway, I'm actually a substitute speaker for an event that got canceled, but let's get started with what I'm going to present with you. So I'm going to sit down because I'm too big to stand the whole thing. All right. Early major problems, okay. In the winter of 1997, okay, Java had a servlet API firmly in place, it had a JDBC API firmly in place, and it had an RMI API fully in place. And with those three little pieces of technology capability, the Java machine from Sun went out and told the world, web applications are ready. Now here's a case where they're to be proven wrong, very dramatically. The week before Christmas in 1997, the web-facing order management system at Amazon.com repeatedly crashed. All right, availability was severely impacted. Millions of dollars in potential revenue were lost. Credibilities with their customers were damaged. And just to put it simply, Amazon.com cannot go down the week before Christmas. That's all there is to it. So that's a big pie in your face for everyone who said web applications are ready, because, well, they weren't ready. Okay, an urgent, immediate solution was required to correct legacy application architectures so they could reliably and performantly operate at internet scale. These architectures that scaled in the data center are going to work when you have millions of simultaneous HTTP sessions coming through the week before Christmas. And not only they're not just surfing HTTP sessions, they're transactional HTTP sessions. So they're depending on back-end systems to transact business, okay? That didn't work in the winter of 1997. So we needed a silver bullet, and we needed it fast, and inter-caching technology. So what is at stake for caching solution providers and their customers? All right, caching technology providers had a huge incentive to deliver 100% sound and 100% complete solution. What was at stake was the World Wide Web as a reliable and performant application platform. 5 important things were immediately needed. We needed to deliver to application architects and developers the capability to rapidly implement the caching provider's solution. Okay, wasn't enough that they could build something. They had to empower existing architects and existing developers to use their solution to quickly build and deploy. They had to offload the database. This was an ultra-urgent requirement. The reason Amazon was crashing was because to commit a transaction, you have to physically touch a disk from a database server, okay? You can't do that with millions of transactional simultaneous HTTP sessions. Your system will fail, okay? They had to deliver solutions so you could scale up. How can I make a cache's in-process heap as big as possible? and they had to scale out. How can I distribute my cache so it can be distributed across multiple processes? And most importantly, they had to generate a confidence that they could buffer against load variability. Amazon.com worked perfectly in 1997 for 51 weeks. Okay, but that week before Christmas, the show stopped. All right, now given that, I want to talk with you a little bit about a brief history of the data locality and latency problem, because this is very relevant to capital markets use cases and their needs for caching vendors. Okay, caching vendors have to supply us solutions that allow us to move our processing as close as possible to the data as possible, and we have to be able to access that data with the lowest possible latency. Physical constraints come into play with our requirements for these use cases. All right, the data locality problem. In a single sentence, it asks this question: how much am I willing to pay to have my data as close as possible to processing resources? All right, the absolute closest you can have your data to processing resources is in the registers and the arithmetic logic unit of the central processing unit. Now, moving the data further away, you can be very close on circuit, on chip, to the registers and the logic units by creating an L1 cache. Okay, moving a little bit further, still on chip, you can have an L2 cache, and you can come off chip, okay, and have main memory or RAM. But you pay a price as you move away. Okay, when you go onto RAM, you have to cross a physical circuit board, a data bus, to get to the central processing logic circuitry. Okay, so, but the motivation for moving the data away is you can accommodate more data. Obviously, you can only support maybe just a few K in the registers, support a few gig in the RAM. All right, moving further away, let's say I have two processes, okay, sitting on a local system, okay. Now, I don't want to have the data so close that I keep redundant copies in each process's user space. Unix has a IPC facility where you can use shared memory between the processes. So that's moving the data further away, even further. Okay, still very close. The price you pay there is you have to go through a kernel API with a system call, like you have to do a shared memory create, shared memory attach, shared memory op. Okay, that's a very clumsy API to work with if you want to work compellingly with data. But again, it's a method of moving the data, keeping it still close to the processing, but not that close. Further still, you have a single, you have three processes now on one platform. Okay, so now I can introduce TCP/IP semantics. All right, this is only one IP address. So if I have a data server listening on port 1521, I can specialize that process for its data needs, and I can keep these other processes small. So that's moving the data further away still. Finally, I can have three IP addresses within a local network. Okay, I have to go through physical network semantics over the same TCP/IP API. But again, this is moving the data further away from the processing at the cost of just a few network hops that are local. Now, finally, I can get a huge data space and use public data sources. Okay, so now I'm using TCP/IP over a wide area network. Now, typically, I won't be allowed to use TCP/IP directly. I have to use an application protocol like HTTP, because most network administrators aren't going to let you use TCP/IP directly on the public internet. So the idea is this: we can accommodate more and more and more data by moving the data further away from the processing, but we're going to pay costs elsewhere that we're not tolerant of in capital markets use cases. Okay, so let's talk about the latency problem. We've looked a little bit at the data locality problem, how we can get more data to process if we move it further away from the processing resources. Given that data is available, how fast can I access it for processing? That's the big question we ask for low latency applications. So let's look at the registers. We can only accommodate like 1 KB of data size. And this is an old chart, but just so forgive it, just scale it up a little bit. The symmetry is the same. But with that data in that, we can access it in 1 to 3 nanoseconds, which is virtually zero time. I'm paying an almost zero cost to access that data. On chip, again, almost zero cost. Even on off chip, it's almost a zero cost. Now, when I go to main memory and I have to cross a physical data bus, I have an order of magnitude jump, but we're talking about 10 to 60 nanoseconds, which is almost a zero cost. Finally, look what happens when we have to go to access on a hard disk. All right. Several orders of magnitudes different. 3 million nanoseconds. Intolerably slow for low latency cases. Now you say 3 million nanoseconds. Now that's only 3 milliseconds. Okay? For some views, 3 milliseconds is acceptable latency, but for us, we don't tolerate it. Okay? I want to give you a little bit of math. Now this looks kind of intimidating at first glance, but it's really quite simple. It gives you a basis for architecting latency solutions given your resources. This is a equation that was first introduced by Vilfredo Pareto, who was an Italian mathematician in the 19th century. And what he was doing was he was trying to get expected return on his Italian real estate speculation. Okay, what he did was he outlined a space where there's n possible events in the space, and each of those n events have a probability of occurring. If you add up the probability of each of the I events in n, that probability adds up to 1. So a complete outcome is determined. Okay, so what we want to do is say, given this model, we want to generate our notion of what expected latency is. Okay, if you take any probability in statistics courses, this looks like what's known as a weighted expectation expression. Okay, so let's say our desk says to us and says, Ben, given the resources you have, we want you to generate a latency solution that gives us an expected latency of 0.4 milliseconds. And I say, okay, well, what are my resources to do that? So they say, Ben, we're going to give you a level 1 tier where you get virtually zero cost. It's going to be on-chip, on-heap latency. We're going to basically call that zero. It's going to be less than 5 microseconds, which we're basically going to call 0 milliseconds. And the other participant in your caching levels is L2, which is going to cost you 2 to 3 milliseconds, which basically acts like disk. Okay. So given this, I want to engineer how much of my resources do I want to put in L1 so that I can meet the 0.4 millisecond mandate from the desk. If I allocate 80% and use this expression, well, 80% times 0 costs, 20% of the time I'm going to have to pay the 3 millisecond cost, so my expected latency is 0.6 milliseconds. Still too slow to meet the 0.4 millisecond mandate from the desk. So I say, well, what happens if I partition 90% of my resources to L1? Then my latency is 90% times 0 is 0. 10% of the times I pay the 3 millisecond cost. So that total value is 0.3 milliseconds, which is better than what the desk asked for. And basically you can stop your allocation right there. I can just go to this, I can get you 0.3 milliseconds if you give me 90% of my resources in L1. That's going to be very expensive to them, but once they hear they can get 0.3, they'll always buy it every single time because it's the milliseconds that are precious. All right, moving down, I want to talk a little bit about the physics of low latency, okay? I'm not really qualified to talk about physics, but let me mention about Wall Street is dominated in this space by physicists. There are 2,000 PhD physicists currently working on Wall Street. It's impossible for the U.S. colleges and universities to meet the Wall Street demand. It turns out that many of these PhD physicists are from former Soviet bloc countries. Now, if you ask these algo quants, and they're at every house, every one of them has all these, they're all bald, they're all male, they all have beards, and they're all from the former Soviet Union. And it's exactly, I'd hate to be non-politically correct, but that's exactly who they are. And if you ask them what they worked on while they were in the Soviet Union, they'll very very calmly and very directly say, we worked on trying to defeat stealth. And I was fascinated by that. I say, oh, did you have any luck with that? No, we couldn't do it. Okay, so it's interesting now that the pride of like Karl Marx and Vladimir Lenin, these people who were trying to defeat stealth and used to design hydrogen bombs to blow us up, they're now here in our neighborhood designing low latency, high frequency capital markets trading algorithms, and they're doing it very successfully. So Wall Street will go to the former Soviet bloc. All's forgiven. All's forgiven. If you bring the talent, we'll bring you the use case. Write us the algorithms. So that's where we stand. It's a very interesting and dramatic. Karl Marx and Vladimir Lenin must be rolling over in their graves. But anyway, let me tell you about some of the algorithms that are famous that they created. They've got really weird names, and I don't know why they're named. But one of them is Cherokee Nation, Marco